Welcome to the Explainer. Today, we're literally unlocking the invisible source code of reality. I'm talking about the hidden rules governing every single physical interaction around us, force, and the laws of motion.
Okay, let's dive into this by asking a surprisingly profound question. Why does the speed of an object actually change over time? And do all motions even require a cause? We see things speeding up, slowing down, and stopping every single day. But the core mechanics making that happen? They're completely invisible to the naked eye.
To get to the bottom of this, here's our game plan. We'll start with the mystery of motion, tackle unbalanced forces and friction, and then break down inertia and the first law. After that, we'll hit momentum and the second law, before wrapping up with our grand finale, equal and opposite reactions.
All right, part 1, the mystery of motion.
So, think of force as the universe's invisible actor. You can't see it or taste it, but it runs the show. And what's wild is that for centuries, philosophers had this completely backwards. They figured, well, if you kick a ball, it eventually stops, right? So rest must just be the natural state of everything. But then, scientific renegades like Galileo Galilei in the 1500s and later Isaac Newton came along and totally shattered that consensus.
Which brings us to part 2, unbalanced forces and friction. And this brilliantly illustrates the core concept, the difference between balanced and unbalanced forces. Picture a wooden block sitting on a table. If you pull it equally from both the left and the right side, meaning the forces are perfectly balanced, literally nothing happens. The motion doesn't change. It's only when you apply an unbalanced force, pulling a bit harder on one side, that this stationary object actually starts to move. Movement absolutely requires an imbalance.
But hey, what about when you try to push a really heavy box and it just doesn't budge? Are you just weak? Well, no. You're actually fighting another invisible force, friction. Friction acts right between those two surfaces in contact, and it perfectly balances out your push. It pushes back. If you give it a light push, friction matches you. You only get that box moving when your push finally overpowers the friction, creating that essential unbalanced state.
Moving right along to part 3, inertia and Newton's first law. Let's picture this brilliant thought experiment by Galileo. Imagine a U-shaped ramp. You roll a marble down one side that speeds up, then it rolls up the opposite slope and slows down until it reaches the exact same height it started from. But Galileo thought, okay, what if that opposite side isn't a slope at all? What if it's completely flat and frictionless? He deduced that without friction to stop it, that marble would just roll forever. It's constantly trying to reach its original height. Basically, an object in motion stays in motion as long as there is zero unbalanced force acting on it. And Isaac Newton took Galileo's revolutionary marble experiment and built directly upon it, formalizing his first law of motion. An object remains in a state of rest or of uniform motion in a straight line unless compelled to change that state by an applied force. It is just such an incredibly elegant rule. Objects simply want to keep doing exactly what they are already doing.
Now, this natural resistance to change, that is what we call inertia. You can almost think of it as an object's inherent laziness. And we actually measure this laziness through mass. I mean, it's pretty easy to change the motion of an empty shopping cart, right? It has low mass, so low inertia. But try suddenly stopping a massive heavy freight train. No way! It has an immense amount of inertia and powerfully resists any change to its state of motion.
And you actually experience this laziness in your own body all the time. Think about it. When a bus suddenly slams on the brakes, your body wants to keep moving forward at that old speed, so you get thrown forward. Or when a car suddenly floors it, your body wants to stay at rest, so you fall backwards into the seat. This is exactly why we need seatbelts. They provide that necessary unbalanced force to safely counter your body's dangerous inertia during a sudden stop.
All right, let's step up the complexity a bit. Part 4, momentum and the second law.
Have you ever wondered why getting hit by a fast-moving table tennis ball just sort of bounces right off you, but getting hit by a cricket ball moving at that exact same speed can cause a serious injury? The answer is momentum. Momentum is this crucial property that combines an object's mass and its velocity, so it accounts for both how heavy an object is and how fast it's traveling. And this brings us right to Newton's second law. This law essentially tells us that the force needed to change an object's momentum depends entirely on how quickly you're trying to change it. The rate of change of momentum of an object is proportional to the applied unbalanced force. Simply put, if you want to change an object's momentum very suddenly, you're going to need or experience a truly massive force. So, the crucial point is this monumental equation right here. F equals ma. Force equals mass times acceleration. This is the mathematical heartbeat of the second law. It basically gives us a really precise way to measure force, just by looking at the mass of an object and exactly how rapidly its velocity is changing.
Let's move to and see how this builds into a practical, everyday example. Watch a professional cricket fielder catching a fast-moving ball. They don't just hold their hands out stiff. No, they catch it and pull their hands backward, bringing the ball to a stop gradually. By increasing the time it takes for the ball's momentum to drop to zero, they dramatically decrease the acceleration. And lower acceleration means lower force, which means they don't break their hand. It is literally Newton's second law in action.
And finally, we've reached the top of our staircase. Part 5, Equal and Opposite Reactions. Newton's third law states, to every action, there is an equal and opposite reaction. I love this one because it shows us that forces are absolutely never solo actors. They always exist in pairs, interacting simultaneously on two completely different objects. You literally cannot touch something without it touching you back with the exact same amount of force. Think about firing a gun. The explosive charge inside exerts this massive forward action force right onto the bullet, pushing it down the barrel. But simultaneously, the bullet exerts a reaction force on the gun that is perfectly equal in magnitude, but opposite in direction. That sudden backward push, that's the violent recoil you feel slamming against your shoulder.
But wait a second. If the forces are exactly the same, why does the tiny bullet fly forward at lethal supersonic speeds while the heavy gun only kicks back a few inches? Well, because equal forces do not mean equal acceleration. Remember F equals ma? Because the gun has a much larger mass than the tiny bullet, that exact same amount of force produces a tiny acceleration on the gun, but a massive explosive acceleration on the bullet.
Now, what's really interesting about this slide is how this concept applies to something as simple as taking a walk. When you step forward, your foot is actually pushing backwards against the ground. And because of the third law, the ground reacts by pushing your foot forward with the exact same amount of force. The Earth is so impossibly massive it doesn't move, but you are propelled forward. So, are you pushing the road, or is the road actually pushing you? Keep that mind-bending thought in your head next time you take a stroll. Thanks for joining me for this explainer, and keep questioning the invisible forces all around you.